All right, round 5, we're back to the graphs, and y'all know that I love graphs, right? So swimmer A swims at constant velocity, takes 8 seconds to finish the race. Let's say we had a camera that took a picture every 2 seconds, right? So we're kind of getting a picture of where this person is with still frames, right? How many pictures would it take, right? 8 seconds. So don't forget 0, so we have 0, 2, 4, 6, 8, 5. 5 points, right? So how am I going to distract? Let's see how many points. We have a point in the middle, point at the end, point at the end. So this is where, if we took a point, we have something moving at constant velocity, what would it look like? I should have had you guys do this, right? So draw the positions, right? We're going to start here. I'll have this position 1, right? Position 2, position 3, position 4, position 5. How did I draw them? Why did I draw them in this way, right? What do we know about the swimmer? Swimmer's moving at constant velocity. What about the dots tells you that it's moving at a constant velocity? Let's think. Velocity is equal to delta x over delta t, right? All these pictures we're taking at 2-second intervals. So that 2 seconds, right? How far you traveled in 2 seconds. That's what all these mean. x1, this is where time is equal to 0. This is time is equal to 2 seconds. Time is equal to 4 seconds. Time is equal to 6 seconds. Time is equal to 8 seconds, right? So that time in between each of these dots is 2 seconds. So what is it that tells me that I'm moving at constant velocity? Well, hopefully you're getting there. It's that displacement. It's not perfect, everybody, but it's pretty close. The delta x between each of these time points is exactly the same. So let's see. 1, 2, 3, 4. 50 divided by 4. So it's all 50 divided by 4. What would that be? 12.5, something like that. So all those displacements are exactly the same length. And so all that average velocity, we could do that right now, right? Let's see, your displacement would be 50 meters total, right? Time would be 8 seconds, right? So you get 50 divided by 8 is equal to 6.25. Velocity is equal to 6.25 meters per second. That's your average velocity. Now, if I did that for any 2 pieces, right, I could do that for x2 and I could do that for x4, right? So let's see, if I'm moving at constant velocity, what position would I have for x2, right? Well, I'm moving at 6.25 meters per second velocity. So my displacement in this case would be, here we go, velocity times time, be 6.25 seconds times, well, how many seconds go between x2 and x4? Or just, well, let's see, or just 2 seconds, right? Because I'm starting at x1 and going to x2, right? So if I start there, every 2 seconds, meters per second times 2 seconds, so times 2, 12.5. All of these, 12.5 meters, 12.5 meters, right? 12.5 meters. 12.5 meters. All of these are 12.5 meters. So if I calculate the average velocity between, which is delta x over delta t, I can calculate that between x4 and x2, which means I'd have t4 minus t2, right? So I have all my locations I would need for that. Velocity, x4, let's see, that would be 12.5 times 3. That location is 37.5 meters minus 12.5 meters all over, well, the time. Let's see, 6 seconds minus 2 seconds. So my average velocity here, well, it's going to be 25 divided by 4, which is 6.25. It's the same. It's the exact same, right? And that's exactly what you would expect if you're moving at constant velocity all the way through, okay? Equal time intervals. No matter which 2 I choose, I'm always going to end up with the same velocity between those 2 points, right? And I see that the distance traveled between those 2 points, given that the time period between the two, between all of these dots is exactly the same. So now if I were to take this, right, we went on a little aside with the numbers, right, but let's get back to the graphs, right? If I were to take all those positions, right, 0, 0, 2, 12.5, 4, 50, 6, 37.5, 8, 50, right? Seconds and meters, right? If I took that and plotted it on a graph, which one would it look like? Hopefully, you got it on the first try, it'd be B. There's 0, there's time 2 seconds, time 4 seconds, times 6 seconds, times 8 seconds, right? So this is x5, this would be like x3, right? And you connect them with the straight line in between because we're assuming we have constant velocity between the two, right? Taking these pictures, taking the data, being able to take the data and extrapolate to what it looks like in a graph, incredibly important task, skill to have, not just for this class, but also I think for any sort of occupation, right? Can you take what you have and represent it in a graphical form and be able to say what it means, right? Okay, so if we were going to draw a velocity time graph for this, what would it look like? Well, here's velocity, time, and my velocity for all of them was always 6.25, right? So the velocity at 1 was 6.25, right? So there we go. 6.25 you start. At some time later, right? At T1, you're still up here at 6.25. T2, you're at 6.25. T3, 6.25 meters per second. Let's see, that's T3, T4, T5, all these different times, right? You're always up at 6.25 meters per second. So what does a constant velocity look like from a velocity time graph perspective? A flat line, right? Flat line, you're always the same velocity at all different points in time. How does that correlate again to that position time graph? Well, slope. The slope of position time for answer B there is positive and constant. The actual value for your velocity on your velocity time graph is positive and constant. All right, a couple more examples here. This one is, well, two different guys here. One is we have my positions going up above. Let's see, this would be where you start right here. Here's your x1, and this would be 2, 3, 4, 5, 6, 7. So here's x7 over there. Give this guy a try. Look at the motion. How would you describe the motion, right? We've only dealt with like constant velocity here, but does your constant velocity always stay the same? And if it doesn't, how is that going to impact the slope? Give it a try. This guy here looks to me like between these points, you're moving at constant velocity, but slow. Over here, it's constant velocity, but fast, right? So how's that going to change? We saw that constant velocity means you have a straight line, but what indicates whether or not you're moving fast or slow? That's the steepness, right? So this one is always the same, right? This one, let's see, would you be moving? If you're moving fast, you're going to have a steep slope, and if you're moving slow, your slope will be shallow. So it looks like we're going from shallow to steep here, right? So it looks like for A, it goes from, this goes from fast to slow. That's not what's going on here. For C, it looks like you're going slow to fast, and here we're going slow to fast. Okay, so how do we do this one? What's different about C and what's different about D? Well, it looks like C, you start at a positive position. Okay. Ooh, there's my origin. It looks like for this one, x1 is a negative. So then that's what happens with D. D, you start in the negative. You start slow, and then you hit the origin. Right when you hit that origin, looks like you're moving a little bit faster there. So there we go. There's D. Okay, for how about same thing for this next one here, except now we want to know about velocity time graphs, not just position time graphs. Oh, you know what? Hold on a second. If I were to come up here, if I did my velocity time graph, what would that look like? Huh? Pause it, try it. Yeah? No? Yeah, pause it, you should try it. But now we're back here. Let's see. Your slope is positive, slope is positive. So you're always moving in the positive direction. Look, your arrows are always going to the right. You're always increasing your displacement. So your velocity is always going to be positive, even though you have a negative position. Slope is positive, and it's constant. Then when you hit this point right there, your slope is still positive, but is a bigger number. So that's the velocity time graph that goes along with this one. Okay, how about this one? Right, there's your x1, 2, 3, 4, 5, 6, 7. Right, there's 7 right there. x7. Velocity time graph go along with this one is. Give it a try. All right, now with this one, velocities. Are they positive or negative? Velocities are negative. Always negative? Yes, always negative, because they're always pointing to the left. That takes out A and C, right? It's always good when you can remove those. Now, what is B saying? What is D saying, right? Remember, farther from the origin, farther from 0 means you're moving faster. So this goes fast to slow. This one goes slow to fast. What's happening here? It looks like I have a smaller line than a bigger line, right? So that means I go from slow to fast, and it's always pointing to the left, which means negative and negative. So I'm right there. So I'm going from slow to fast, fast to slow, slow to fast. D, right there. Let's say I wanted to make this into a position time graph, right? I know my position starts positive and starts really big positive, so I'm going to be right there, right? Now, negative. So it's always a negative slope, right? Because the slope, right, my velocity is negative. My slope will always be negative, so it's downwards. It starts slow, then it goes fast. So that means my negative slope will start. Will it be steep or will it be shallow? It's going to start shallow, and then it will go steep. Right? So we start with something that is shallow, and then steep. And there you go. Huzzah, guys, graphs. So good. All right, on to the next one. Unless you need to replay to help you, it's always a good thing to replay. I don't hold against anybody. Actually, I encourage it. Onwards.